the one that's a little more difficult. So remember what we had yesterday. If you guys are not in physics, don't worry. You'll still get it, I think. So what we had yesterday is we had a capacitor and we had a resistor. So the capacitor had some value C and the resistor had some value R. And we charged the capacitor up so that there was a voltage across the capacitor, some initial voltage. And if you remember what we plotted, if we plotted voltage versus time, it looks something like that. So we know it's an exponential decay. So the way you work these problems is you look at the relationships that are associated with each part of the circuit. So for the capacitor, we know that the capacitance is equal to the charge divided by the voltage, or the potential, electric potential. And for the resistor, it's called Ohm's law. And Ohm's law says the resistance is the voltage divided by the current. So what we would find out is if you plotted charge versus voltage for a capacitor, you would get something like that. So the higher the voltage you apply to the capacitor, the more charge you get in the capacitor. For a resistor, if you have current and voltage, if you increase the voltage, you increase the current. And in this case, the slope of the line is the resistance. So it's the other way around. It's 1 over the resistance. Yeah, because if you think about this, if you made it into a equation, V is equal to R times I. So this is it. Yeah, so you can switch them around here. I'll put voltage up here, current down there. Still a line, but this would be, the slope is the rise over the run, and the rise is the y-axis and the run is the x-axis. So the slope of this line is the resistance. They're both linear. Now we haven't covered this yet in physics, but the current through a wire is equal to the derivative of the charge with respect to time. So what current is in an electric circuit is how many charged particles pass through a wire for a given amount of time. So the more charges that are moving, just like water flowing through a pipe. So the more charges that flow through a given area in a given time, the more the current is. So it kind of makes sense, current, how quickly the charges move. So another thing we'll learn later on is that if you have an electric circuit and you have electric circuit, meaning that it's round, or you can go from one part to another. So let me just demonstrate that. So if you went from this point, let's say point A, and you went along this wire through the resistor, along the wire through the capacitor, that the voltage that you start with here is the same voltage that you end up with there. So any voltage change across here has to be equal to the voltage opposite to the voltage change across there. So when I get back to the beginning, I don't have any change in voltage. It's kind of like if I was on a mountain and I staked a point in the mountain and I said, okay, I'm coming back to that point. I could go down the mountain, around the mountain, back up the mountain. But when I came back to where the stake was, I'd still be at the same elevation. So you can kind of think of voltage as elevation. And the path that you take is the circuit that and you can go on steeper parts, you can go on not so steeper parts. So you know the resistance is kind of like whether your resistance would be kind of walking up a steep hill, or even the light. Is the larger the resistance, the steeper the hill. Okay, so what we can do is we can sum the voltages around this circuit. So let's start at A. So what will happen is we'll go through the resistor. So we'll look at the change in the voltage across the resistor plus the change in voltage across the capacitor, and that has to equal 0 because the total change has to be 0. Okay, so the change in voltage across the resistor is going to be equal to minus R times I. Now I'm going to put this as a small, as a time varying quantity, because this is a time. When we looked at the voltage yesterday, the voltage is varying with respect to time. So I'm using Ohm's law to figure out what the change in voltage is. It's going to be the resistance times the current, and if that current changes with time, then the voltage is going to change with time. Now across the capacitor, you've got this relationship. So voltage is equal to C times Q. So that's going to be C times, that's not right. It's equal to Q divided by C. Okay, so it's going to be, so what we do is we switch these. So this goes to the denominator, that goes to the numerator. So it's going to be Q divided by C. And it's going to be Q as a function of time divided by C, and that equals 0. So I've got I as a function of time and Q as a function of time, but the current is the derivative of Q with respect to time, so I can replace the current with dq of t dt plus Q of t divided by C equals 0. Try to get rid of that thing. How do I get that thing? Okay. Go away. Okay. And if I rewrite dq dt as q dot, I'll get minus r times q dot plus, or q prime, sorry, q prime times q of t over c equals 0. Okay, so there's my differential equation. So I've got the derivative of Q, I've got Q, my right hand side in this case is just 0, so but it's a first order linear differential equation. It's not in standard form yet, so we're going to now convert that to standard form. So we'll divide everything by negative r, so we'll get Q dot Q prime, sorry, dot's used as a derivative. I'm getting my minus Q divided by R times C equals 0. So now it's in standard form. So what do? I identify P of, in this case, P of Q instead of P of X. That's equal to negative 1 over RC. That's the coefficient in front of Q. So then you can calculate the integrating factor. The integrating factor is e to the integral of p of x dx. So we stick in p of x being negative 1 over rc dt. It should be t really. So t. It's actually a function of t, sorry. So I'll make it a function of t. All those are functions of time, dt. Okay. So these are all constants, so what you end up with is e to negative 1 over rc times the integral of dt, and the integral of dt is just t, so you get e to the minus 1 over rc times t. So that's my integrating factor. And all of the integrating factors we've done so far have been something like where we've had the natural log result from this integration. But in reality, a lot of them end up having e raised to some power, which is this case. Okay. So that's my integrating factor. So what we do with the integrating factor now is we multiply the differential equation in standard form by the integrating factor. So let's add, so we're going to take this equation and multiply by the integrating factor, which is e to the minus 1 over RC times t. So we get e to the minus 1 over RCT q prime minus e to the minus 1 over RC t. So that's that divided by RC equals 0. So I've just multiplied this by that and this by that. And again, we can always check to see whether we did this right. And if you take the derivative of this, you'll get the second term minus the q part, which I apparently left out. So let me put that back in. I'm glad. So we forgot the q. Okay, this is that q right there. So if you take the derivative of e to the minus RCT, using the chain rule, the derivative of negative 1 over RCT is just negative 1 over RC, which is what I have, a negative 1 over RC. So it is the first term, the first part of the second term is the derivative of the first part of the first term. So it works out. So then I can combine those two into a single derivative. So you get e to the minus 1 over RCT times q quantity prime equals 0. Okay, then you integrate both sides. So we put a dt here, and the integral of 0 dt is just an arbitrary constant. So you don't have any, if we had 1 here, it would be q, or it'd be t. But we don't have anything. So the integral of 0 to t dt is the arbitrary constant. And the right-hand side becomes e to the minus 1 over RC t times q equals c. And then if we solve for q, q is equal to c divided by e to the minus 1 over RC t. Okay, so that's the solution. As a function of time, q is equal to c divided by 1 over c over e to the minus 1 over RCT. Now, we have to apply our initial condition to get the final solution. So the initial condition is that at t equals 0, q is equal to the original amount of charge on the capacitor, which is equal to, if we go back to the definition of the capacitor, the charge is going to be the product of the capacitance and the initial voltage. So that's going to be equal to C times V0. The initial voltage, it was 6 volts yesterday when we used the thing. So the initial voltage would be 0. Okay, so we'd say Q is equal to, for Q we put in C times V0. For T we put in 0. And so we'll get C divided by e to the 0 power. This is a difference. This is capacitance. Let me put C1 here because otherwise we'll get C's confused, which I've already done. This is capacitance. That's the arbitrary constant. So let me make sure we're going to solve for the arbitrary constant. So C1 is equal to C times V0. So if I plug that back in here, I'll get Q is equal to C, which is C1, which is the capacitance times the initial voltage divided by e to the minus 1 over RC t. Now I've realized I've made a mistake somewhere because we should have something that's an exponential decay. And if I move this to the numerator, it's going to become positive, and it's going to become exponential growth. So where did I have to figure out where I made my mistake? It's a sign error somewhere here. And so let me go back and look at this. So we'll go back, and now that we've done it, we'll check everything out here. So we had the loss in that, we had the increase in voltage, dq dt equals I. I'm not sure where I made a mistake here. So I may have to come back to this on Thursday because I don't see it right now. But you can kind of see how we end up. I've got a sign error here somewhere. And, ultimately, when I do it correctly, which I'm not sure what I did wrong, I should have this. I should have minus 1 over RCT. And then the voltage is just equal to the charge divided by the capacitance. So what I end up with is the voltage as a function of time is going to be equal to V0 times e to the minus 1 over RCT. So that's what we saw yesterday, is we saw that at t equals 0, that the voltage was equal to the initial voltage, because that e to the 0 is 1. And then as t grows, this thing gets smaller, and so the voltage drops, and it drops in an exponential form. And we were asking the question, we used K yesterday. We said, was K equal to R times C, R divided by C, C divided by R, or 1 divided by RC? Well, it turns out from solving the differential equation, it's 1 over RC is the K. We could have figured it out from the data yesterday, kind of give us an idea by just taking a point in time and assuming that it has this form, because it looks like an exponential decay curve, and we could have figured it out using the stuff we learned in section 2. But this is finding out mathematically what the exponent is. So anyway, I'll tell you where I made the mistake on Thursday. It's just like I said, it's a sign error somewhere, somewhere about here, or well, back here. It has some. Yeah, it's probably right in here, and it's the assumption that I've made regarding one of these two signs. And it seems to make sense to me, but it doesn't work out, so I know there's something wrong. Okay, moving on. Here we go. Okay, so the last thing we're going to talk about in this chapter is something called Bernoulli's, how to solve Bernoulli's equations. And the so the Bernoulli's equation looks very similar to what we've been solving relative to a first order linear differential equation. The only difference is, instead of just having q of x on the right hand side, we have this additional term which is a nonlinear term involving y. And it can be y raised to any power. So what we've been looking at is y raised to the 0 power, and y raised to the 0 power is 1, and you just default back to the first order linear differential equation. But if if the exponent is anything other than 0, then we call it a Bernoulli equation, and we basically have to make a substitution. We have to do some manipulation, make a substitution, solve the first order linear differential equation with a variable other than y and x, solve it, and then resubstitute the substitution we made to make it back in terms of y and x. So how do we do this? Okay, so this is the same as that, except the letters are lowercase instead of uppercase. And we can't do this when we use this when n does not equal 0, which is just a normal first order linear differential equation, or n equals 1, because if n equals 1, then you can combine these two because they'd both be just y. So it's for other cases where n is either not equal to 0 or not equal to 1. So what we do is we divide the equation by y to the n. So whatever this nonlinear term is, we divide every term in the expression by y to the n. So what happens is the right-hand side, instead of being q of x times y to the n, just becomes q of x. So we have our derivative divided by y to the n. We have our function divided by y to the n. We have this not divided by anything anymore. And then we define a new variable, just like we did with the homogeneous equation. And the new variable we'll call v instead of new. And v is equal to the ratio of y to the thing we just divided by. So if you look back at the modified version of the original equation, p of x is multiplied by y over y to the n. So we're going to, instead of have p of x times y over y to the n, it's going to have p of x times v. The problem is we got to also do something with the first term. So to handle the first term, we take the derivative of this thing so that we're going to get a y prime involved in that, but you'll see in here in a second. So let me. Okay, so what is v prime? How do we make this substitution? So let's show you how it works. Okay, so I'm gonna work through what we've done so far, and then I'm going to show you how you make this substitution. It's easier to do it with an example. So this is a Bernoulli equation because I have the derivative, I have the linear term, I have the nonlinear term. So what we're going to do is we're going to divide by y cubed. So if we divide everything by y cubed, we'll get y prime over y cubed plus 3x squared times y divided by y cubed. And that's equal to x squared. Okay. Now, here I have y over y to the n. I can simplify this. This is equal to 1 over y squared. So you can always cancel out one of these with the appropriate number of the stuff you're dividing by. Then what we're going to do is we're going to, let me add a page here. So what we're going to do is we're going to take the derivative with respect to x of 1 over y squared. And why are we going to do that? Because that is equal to this, the new variable. We're letting v equal 1 over y squared. So to be able to rewrite this equation in terms of v instead of y, I'm going to need, for this part, I'm going to put v in, and I need v prime to make the substitution to eliminate this part of the expression. So let's just do it. So you have to use implicit differentiation because I'm taking the derivative with respect to y, the derivative of y with respect to x. So, but we're going to rewrite this as a fraction or as a exponent where we've moved things to the numerator. And the derivative of y to the minus 2 power, you take the derivative, you take the exponent, multiply by the variable times the exponent, or the exponent reduced by 1. So we reduce this by 1, we make it one more negative. And then you multiply by y prime because it's implicit differentiation. Now, after I've taken this derivative, I'm going to move this back to the denominator. And I'm going to divide both sides by -2. Okay, now, notice this process here has resulted in that term. Oh, how'd that happen? Get off there. So this is equal to v. I take the derivative of this over here to get v prime. In the process, I end up with the exact term that I need to substitute for in the original differential equation. So for this, I'm going to substitute v prime over -2. And for this part, I'm going to substitute v. So that's the next step. So let me extend my page a little bit here. So this equation is going to be equal to v prime over -2 plus 3x squared times v, and that equals x squared. And if I multiply every term by -2, I'll get v prime minus 6x squared v equals x squared. So I messed up there. I forgot to multiply this by -2. So -2. So we get -2 x squared. So 3 times -2 is -6. 1 times -2 is -2. And so my original differential equation was not a first order linear differential equation, it was a first order nonlinear differential equation. But by making this up, going through this process, I now have a first order linear differential equation in v. So I can now solve this equation using the integrating factor. So when we had homogeneous equations, we had a non-separable equation. We made appropriate substitutions so that in the new variable it was separable. Here we make this substitution so that the original equation, which was not a first order linear differential equation, by making this substitution I have converted it or transformed it into a first order linear differential equation, which I do know how to solve. So let's solve this. And so we're going to say p of x equals -6x squared. So that's the coefficient in front of the v term. The integrating factor is e to the integral of p of x dx. So I plug in p of x in there. So I get -6x squared dx. I integrate this. So when I integrate it, I divide by I add 1 to the exponent, divide by the new exponent. I don't, and this is e, so e to this integral. So take the constant out, add 1 to the exponent, divide by the new exponent. I don't add an arbitrary constant. So if I simplify this, I'll get e to the minus 2x cubed. So that's my integrating factor. So now if I take my first order linear differential equation in standard form and I multiply by the integrating factor, so all I'm doing is taking that integrating factor, multiplying everything, I'll get e to the minus 2x cubed v prime minus 6x squared e to the minus 2x cubed v. And then the last term here equals -2x squared e to the minus 2x cubed. Now, if I did this integrating factor correctly, the derivative of this should equal that. And if you think about the chain rule says you take this term, which is right here, and then you multiply it by the derivative of the exponent. Well, the derivative of the exponent is going to be negative 6x squared, which is what we have here. So it is. So the derivative of this equals that. And the derivative of that equals that. And therefore, I can combine the two terms into a single term. So the left-hand side, there's a chair here. So the left-hand side becomes e to the minus 2x cubed v quantity prime is equal to negative 2x squared e to the minus 2x cubed. Okay. Then we integrate. So we integrate e to the minus 2x cubed v quantity prime dx is equal to the integral of negative 2x squared e to the minus 2x cubed dx. And the integral of this is just the term in the parentheses. And the integral of this, you have to use u substitution. So you'd let u equal the exponent. So you get du is equal to negative 6x squared dx. What I have here is x squared dx. So I need to solve for that. X squared dx equals du divided by negative 6. So let me move this down a little bit. So this, if I factor out the negative 2, I'll get e to the u times du divided by negative 6. So you factor out the negative 6, simplify it, you get 1/3. Integral of e to the u du. And the integral of e to the u du is e to the u. We add our arbitrary constant at that point. Then we substitute u back in. So that was equal to, what was equal to negative 2x cubed plus c. Okay, so that's the solution of the first order linear differential equation that involves x and v. And then I have to go back and plug v back in. So the v was equal to 1 over y squared. If we go back and look at that, yeah, it's complicated. That's why I don't put it on a test. But so where do we do it? We said somewhere here. Yeah, v is equal to 1 over y squared. So okay, we'll stick this back in. This is when you're glad you're not an engineer. Okay. So then we know that v is equal to 1 over y squared. So we plug that back in. So you get e to the, sorry. So making that substitution, you get e to the minus 2x cubed times 1 over y squared is equal to 1/3 e to the minus 2x cubed plus c. Ta-da! There's your solution. Yeah. Now I could solve for y. You could do. If you had some initial conditions, you could solve for c, and you could solve for y. It's going to be you'd have a plus or minus solution. If you took the square root of that thing, but you could do the rest of it's algebra. So let's review what I did here because there's a lot to absorb. Okay, so here we go. You start with a differential equation that's nonlinear, but because the term on the right-hand side is the special form, we say, hey, it's a Bernoulli equation. There's a procedure for that. So we divide the entire equation by whatever this nonlinear term is. We take the term that is just y divided by this nonlinear term. That's our substitution. So y over y cubed, which is 1 over y squared, is equal to our substitution variable. We take the derivative of both sides of this, which we did over here, so that we can end up being able to substitute also not just for here, but for here, to put this part in terms of v prime instead of y prime, which we did. Usually it always involves v prime and some constant. So you make those two substitutions. 1 over y squared is v. This is equal to v prime over negative 2. When you do that, the transformed equation becomes a first order. I got to go down here. So when you make that substitution and you put it in standard form, you now have a first order linear differential equation in the variable v. So we know how to solve first order linear differential equations. It's by using the integrating factor. So we take the coefficient in front of v, which is p of x, and that's the integrating factor is equal to e times the e to the integral of p of x dx. So we integrate whatever this thing is. That's the exponent. Again, because there's no natural log involved, you just end up with e to something. You take that integrating factor, multiply the first order linear differential equation in standard form by that integrating factor. If you do everything right, the derivative of this should equal that, which it does. So you can combine those two terms into a single product. So we're using the opposite of the product rule here to combine those two. So that we did that. We multiplied the right-hand side by the integrating factor as well. So once you've simplified the left-hand side, then you can integrate both sides. When you integrate the left-hand side, you just get rid of everything except what's in the parentheses. That's the easy part. The right-hand side, you just have to do normal integration stuff that you've learned and already forgotten from first semester. So you go through here. In this case, we had to use u substitution because that integral is not in the table, but I used the exponent as u and made the appropriate substitutions and did the integral, substituted u back in, and I ended up with the solution in terms of x and, where's my cursor? Can't find it. So I got my solution in terms of v and x here. But what I really need is to get in terms of y and x. So then I go back to my original substitution and make that substitution for v, and now I get my final answer. Okay, so that's kind of how it works. Okay, so I'm going to do one more, and so here's another one. So again, it's not linear because I've got the y squared term. But I am going to put it in standard form for a Bernoulli equation. So you get y prime minus 1 over x times y is equal to negative y squared. So all I've done is move that to the left-hand side. Okay, divide by y squared, because that's the nonlinear term over here. So I'll get y prime divided by y squared minus 1 over x times y divided by y squared is equal to negative 1. I'm going to go ahead and simplify the second term here. So y divided by y squared is just 1 over y. Okay, now this term that involves y we're going to call v. v is equal to 1 over y. So I'll end up with negative 1 over x times v. But I need to make the appropriate substitution there. So what I say is v prime is equal to the derivative with respect to x of 1 over y. But I have to rewrite 1 over y as y to the minus 1 power, so I can use the power rule. So I'll get, when I take this derivative, I'll get negative 1 times y to the minus 2 power times y prime. Got to remember the y prime in there because it's implicit. And so what I end up with is negative y prime over y squared. So v prime is equal to negative y prime over y squared. And that should look pretty close to this, except because of a sign or a factor. What I'm trying to get is y prime over y squared, and I've got negative y prime over y squared. So what I need to do is just multiply both of them by negative 1, and you'll get y prime over y squared equals negative v prime. So here's the two substitutions. This is 1, okay, which will be used here. And this one will be used there. So when I do that, this is going to become negative v prime, and the red one will become v. So now I started out with a nonlinear first order linear differential equation. Now I've ended up with a, well, it wasn't first order, it wasn't linear. So this is nonlinear. By doing this substitution, it's now linear. So then you solve that equation using integrating factors again. So first thing you do is put it into standard form. So I've got to just divide everything by negative 1. So that's that. Just change everything negative to positive. P of x in this case is 1 over x. The integrating factor is e to the integral of p of x dx. So you get e to the 1 over x, the integral 1 over x dx. So I just see what this is, plug it in for p of x. The integral of 1 over x dx is equal to the natural log of the absolute value of x, which is just x. Now I did take the absolute value off, which is legal. I never quite fully understand why that is, but we're just going to assume it's legal. So we're going to take the absolute value off. So that's my integrating factor. So then I multiply my first order linear differential equation in standard form by the integrating factor. And this should have been v right there, sorry. Okay, so we get that. So what happens is we get x times v prime plus just v is equal to x. Because x times 1 over x is 1, and x times 1 is x. Okay. So does the derivative of this equal that? Yeah. Well, the derivative of x is 1, so it does work. So that is the proper integrating factor. So that does mean that I can combine those two terms on the left-hand side. So I'll end up with x times v quantity prime is equal to x. Okay, just combine those two into one term. Then we integrate both sides. The integral of this thing is just the term in the parentheses. The integral of x dx is x squared over 2. and we add our arbitrary constant c. So now we have the solution to this differential equation, but we want the solution to be in terms of x and y, which was the original problem. So we go back and look at what what v was equal to. I always forget by this time. So we go back and look, and we see that v is equal to 1 over y. So v equals 1 over y, so we plug that in, so you get x times 1 over y is equal to x squared over 2 plus c, and there is your answer. Okay. So I'm going to have you do a couple of homework problems like this, just because, yeah, it gets complicated, and you probably will need some help. I don't put it on the test, but it just gives you a feel of how this whole concept of solving differential equations, basically you have two ways of solving them. You have separation of variables and you have integrating factor. If the equations don't fit those two methods, then you try to come up with some way of manipulating the original differential equation so that you can fit it into those two solution techniques. And the two ways are, we can, for homogeneous equations, we can convert it by using the appropriate substitution. And for Bernoulli's equations, we have this procedure that works. It is fairly complicated, a lot of steps, but it is doable. And once you do a lot of them, you get good at it. So if you're a math major, I don't ever remember solving Bernoulli's equations as an engineer, so even as an engineer you don't necessarily know how to do this, but at least you get a concept of the complexity sometimes of this whole thing. Okay, so have I assigned section 4 yet? I can't remember. Homework? I'm pretty sure I have, right? If I haven't, I'm going to put it up. So the test is next Tuesday. I don't know if I mentioned that. So we're going to